Good afternoon. Can you all hear me? Because it's really loud up here. So first of all, thanks for being here. Thanks for your support of the EWRE program, and all of you for coming and continuing the effort in building a strong community of scholarship, collaboration, and friendship. Thanks for attending today, not just because you're here today, but for sharing Des and Alice's hope that you will be here annually for years to come, because this is the first annual Lawler Lecture. As many of you know, or some of you know, Des and Alice can't be here today because they tested positive for COVID yesterday and today. And while it's heart-wrenching that they can't be here to share this inaugural lecture, I know that they will be incredibly pleased to see so many former students, UT colleagues, and members of the environmental engineering community. Just to get a feel, how many former students are here? Wow, awesome, that's just awesome. How many UT colleagues? There they are. That's awesome too. And finally, how many people are here because they're part of the environmental engineering community of Austin or Texas? And that is incredible. So thank you guys. This is being recorded, so Alice and Des, as soon as they're feeling better, will be able to enjoy those hands raised and just seeing the type of support that this program has. You know, over the past few days, I've realized that I was not appreciating this lectureship nearly enough over the past year. Des and Alice have worked hard to reach out to all their students, all of our students, the community, and raise funds for this lectureship. And while we have several other endowed lectureships that bring great guest speakers who educate us and inspire us, like Dave Reckhow will in a few minutes, this lectureship is more than that. It's about maintaining the EWRE community and spirit that has been the cornerstone of our program. It's a lectureship designed to bring us closer together in learning and friendship. It's designed to leave a legacy that all of us and Des and Alice's children and grandchildren and future generations can appreciate. And I think we have Kate and Patrick Lawler, who are here today and who, spoke some words last night at the dinner, really reminding us of how important this community has been to Des and Alice and how important we are to them. When Des came to UT in 1980, he and the other new faculty, including Howard Liljestrand, David Maidment, Randy Charbonneau, all around that time, basically ushered in a new paradigm for our program. Des led the transformation of an outstanding program that previously focused on the process design to one that is rooted in the application of fundamental knowledge to applied engineering. For people who want to go on in research, for people who want to go on in academia, for people who want to work in consulting and treat the waters that we now face as water scarcity, water reuse, and other issues face us. And of course, I can't not mention PFAS, because who would want to not go to a seminar and not hear about PFAS? But the really inspiring thing is the community that grew both in academic breadth and diversity. Des helped recruit faculty like Jerry Spitell, Rich Corsi, Dane McKinney, and others. And Jerry and Des worked to recruit Carrie, Kinney, Mary Jo, Kirsitz, and myself, bringing the first women to our program. All of us then worked to bring the outstanding faculty who stand before you now in our classrooms and lead our research vision. It's an amazing program, and it's great to be part of, and all of you are part of it too. DES's own teaching and research program have been marked by a dedication to research and teaching, with nearly 100 MS and 33 PhD students whom he mentored, having been elected to the UT Academy of Distinguished Teaching in 1997, and becoming the Association of Environmental Engineering and Science Professor, Charles Amelia Distinguished Educator in 2012. Charles Amelia was DES's advisor, as many of you know, and that award probably meant more to him than any of the others because he was so fond of the mentorship that he got from Charlie. Also, ASP honored DES with the outstanding contribution to environmental engineering education in 2015 in recognition of his widely adopted book, Water Quality and Engineering, Physical Chemical Treatment. DES's research accomplishments have impacted the design of operation of water treatment plants and our fundamental understanding of water treatment processes. He served as the AESP Distinguished Lecturer, where he had the opportunity to share his research and, more importantly, provide mentorship to many undergraduate and graduate students across the U.S. His accomplishments in research, education, and mentorship continue and still have a profound impact on generations of engineering students, colleagues, and professionals. I want to read a little bit from the pamphlet because we wrote it. I started the process. My colleagues helped edit it, and of course, Des edited it. But Des's contributions to EWRE go well beyond science and education. Des embodies a model of academic success that sets the standard for faculty to emulate across the country. All of us who've been here know that. We've sat in his classes, we've talked to him about research, we have worked with him, learned with him, and shared friendship. In addition to his commitment to teaching and research, he spearheaded the EWRE program's goal of fostering strong relationships among students, faculty, and alumni. His efforts led to the close-knit group that we have in our community in which academic work, softball, I have a confession, I've played softball once while I was here. I hate softball. I love sports, but softball isn't one of them, but it even got me out there. But there's many other social activities that are embedded in this culture, and he was part of almost all of them while he was here. Initiating these relationships with incoming students each fall was fostered by the annual welcome party that Des and Alice hosted many years of his 40-year career. And the whole idea about this lectureship that this excellent fund wants to maintain is the synergy of high-quality academic work and strong community culture. This is the gift to all of us. This is what he wants his legacy to be, and what we are committed to ensuring is a gift for all generations of EWRE students as we move forward. So thank you for standing together today to honor Des and Alice's love of this program and the community that he has fostered. So next on my speech comes this part where it says, with that, I would like to introduce Jerry Spytel, Associate Dean for Academic Affairs and UT faculty member, to introduce our inaugural Lawler Lecture. Well, unfortunately, Jerry's mother was admitted to the hospital last night, and he flew out this morning. So not only do I provide you the welcome to everyone, I'm going to introduce Dave. And fortunately for you, or perhaps not, Jerry sent me an email this morning with the intro comments. The first thing I'll say is, on my own, I thought of this. It was really nice of Dave Reckhow to grow a beard. It's the first time I've ever seen him with a beard, and I think he did it in honor of Des's beard. And I have to tell you, that's a really nice beer. But, you know, Dave Reckhow has a long history with this program. I think it actually started with Mary Jo Kiersitz. They lived a few miles apart in Buffalo, in a town that I won't pronounce correctly, so I'll let him do that. But they were, you know, and they have worked together since. But in the meantime, in between being raised in the same town as Mary Jo, Des knew Dave from UNC, Chapel Hill, where they were both students. Jerry Speitel and Dave were entering graduate students in 1978. They entered together, and it turned out they worked on the same research project. And it was during a time when there was an Arab oil embargo, 1978, if you remember. Some of you may remember that. Some of you weren't born, so that's okay. But we were trying to get energy independence. This may sound familiar, right? And the big solution for us was fracking. Well, at that time, it wasn't fracking, it was coal. And so I don't know if any of you have ever worked on coal gasification wastewaters. They're nasty, that's a quote. And they were trying to look at biological degradation of coal gasification wastewaters. And this is a quote too. They had some success, but fortunately for humanity and the environment, large-scale coal gasification never happened. So maybe people will say something about that in 20 years at this lecture about fracking. Oh wait, it happened, but we'll see how things go. By then, maybe we'll all be on renewable energy, and fracking will be history, and we'll be looking at other wastes and other waters and other ideas. And by the way, I have nothing against fracking, so I have no political opinion on that. About the same time, one of the big things that was also happening in water is concerns about trihalomethanes being formed in drinking water. And it was, at that time, trihalomethanes were an emerging concern. And so Dave and his advisor, Phil Singer, decided that Dave's skillfulness in identifying chemical reaction mechanisms and pathways and uncanny ability to get his analytical instruments to work and actually meet their detection limits should be applied to DBPs. And so Dave has spent a career looking at disinfection byproducts and other emerging contaminants. And today he's going to speak to us about new challenges posed by toxic organic compounds in drinking water. And with that, I'd like to introduce Dave Reckhow, the inaugural Lawler Lecturer.
Thank you. Okay, I'm going to move this just a little bit. So first of all, it was Tonawanda outside of Buffalo. I hope you can all hear me. And I really am happy to be here, and especially this first chance to honor Des, and I'll say more about that toward the end. But I want to take you on a little bit of a trip and show you a bit of what we've learned about this issue of disinfection byproducts and how disinfection byproducts has changed the way we engage in drinking water treatment and what the future might be and where it might be going. But first, let me say that this is just one of many possible topics of toxic substances in water that one could talk about. And here are three of my favorites, and Lynn talked about one of them, PFAS, perfluorinated compounds. But first, these are areas of great interest to us in the drinking water field, and a few of them you probably know about, have heard about. Lead in drinking water, going back to Flint, Michigan, and the crisis there a few years ago. Before that, Washington, D.C., more recently, Chicago, and in fact, it's a little bit everywhere. And a picture from the front page of Time magazine at the time of the Flint water crisis. The other perfluorinated, per and polyfluorinated substances, PFAS, which we're now finding everywhere. And these are also toxic. And many of you may have seen, in fact, the movie Dark Waters. Well, that's one that's about DuPont Chemical Company and the contamination in Parkersburg, West Virginia. The third one that I bring out here are the disinfection byproducts. And that's what I'm really going to focus on today. The other two have made major news. People are aware of them. They're in the media, either on the front page of major magazines or there are major motion pictures about them. But as far as I know, DBPs haven't been the subject of a major motion picture or appeared on any major magazine. So it's a little bit hidden. All three of these, though, are problems of our own doing. Lead come from our use of lead as a great plumbing material, and lead service connections from mains to homes, and lead solder. PFAS is something that we use in firefighting foams and all kinds of different home products. And DBPs are produced inadvertently by treatment of drinking water with disinfectants, notably chlorine, but really all disinfectants to some extent form DBPs. So not enough time to talk about all three, but I'm going to talk about DBPs because as Lynn said, that's been a major focus of my career for many, many years, starting way back in 1978 at University of North Carolina. All right, so I want to just give you a little preview of what I want to tell you and try and convince you. Number one is the key message is that to solve this problem that we have that's affecting water treatment, we need to treat natural organic matter, which are the precursors to DBPs, and DBPs themselves as the complex mixtures that they are. And so I'm going to go over this a couple of times. And for those of you who like whimsical questions, I got a few of those too. Such as, do trees cause cancer? In other words, was Ronald Reagan right many years ago about trees? Or do analytical instruments for testing of water, are they a benefit or a scourge? Well, it sort of depends on your perspective and whether you're actually running them or not, maybe. Can Chinese hamsters tell us how to operate water treatment plants? Possibly, these little guys. And where in a city do you find the safest water, too? And we'll want to think about that a little bit. Okay, so let's jump into the problem. But we can't jump into it today. We have to go back in time, back to the mid-1800s. And someone that maybe a lot of you have heard about, especially if you've studied water, is Dr. John Snow. And he lived in London, in the Soho district of London, around 1854 during the third great pandemic of cholera that was sweeping across Europe at the time. And he was the one who kind of figured out that there was an association between your residence, where you live and where you drink your water, and whether or not you're likely to get cholera. Cholera is a terrible disease, by the way. You could die very quickly by cholera if you weren't treated through dehydration. And he made this map that has variously been called the ghost map, or has been treated in some major bestsellers that you can find in lots of bookstores. He's very celebrated. And he, at a time when we really didn't understand the germ theory of disease, where we thought that diseases like cholera came from miasmas, bad air, or maybe even just sheer laziness, you would get the disease. There are all kinds of ideas how this spread. He came up with the idea that it was a waterborne disease. And I had the chance recently, just about a month ago, to visit the location where he found the offending pump well that was being used, that was spreading the disease in the Soho district of London. This is a picture my wife Kathy here took of me next to a reproduction of the pump on Broad Street, where John Snow worked and identified the source. But like so many of these great discoveries where the advancement is attributed to usually some white guy, there are there really is a woman who did so much more 20 years earlier that is far less well known than John Snow. And this is Kitty Wilkinson. And I don't know, have any of you heard of Kitty Wilkinson? A few. Yeah, not many. There are no major bestsellers written about Kitty Wilkinson. Yet, 22 years before John Snow made his discovery during the 1854 epidemic, she was up in Liverpool during the prior pandemic in 1832 and was recognizing that you could solve some of this cholera problem by careful washing and especially use of chlorine. And so she not only administered to the poor and the sick much more than John Snow did, but she also recognized that chlorine could be one of the potential solutions to this horrible disease. And so she risked her life going into the slums and doing this work. And she set up what was probably the first public wash house anywhere in the world. And then from that point on, there were many, many more that were established. So this, John Snow, Kitty Wilkinson, were two of the major figures that helped us understand that there was this connection between disease and water. And we needed to do something about it, and chlorine was a potential solution to this. So fast forward about 50 years or more, and now we're starting to really take action at a community-based level and using filtration, but also chlorine disinfection to kill pathogens in drinking water. Here's a figure showing just one of those pathogens, typhoid fever, and showing how successful we were at getting rid of this out of drinking water. 100 years ago, if we had this many people in the auditorium 100 years ago, there would be several of you who would have known someone who died probably from drinking contaminated water. I doubt if there's anyone in this room now who knows someone who died from drinking contaminated water. And this is the triumph of environmental engineering, and thanks to the people who came before us. And so by the 1940s, we had pretty widespread use of good treatment, what we call conventional treatment now, with a filtration and with some sort of disinfection. And that's the great news. The not so great news was that it comes with a little bit of a cost. We don't want to negate the benefits of using chlorine, but a beer chemist from Amstel Brewery left his job in the late 50s and went to work in Rotterdam Waterworks in the early 60s. His name was John Roque. And he went to the town board and asked for money to buy a Carlo Erba GC back in the mid-60s. He wanted to do it because he had been working in the beer industry looking at headspace analysis for flavor purposes, and he wanted to see what happened with the Rotterdam water because there were some complaints about the taste. And so he managed to convince him after a little while, and when he did the analysis of the raw water and compared that with the treated water, what he found was that there were at least 4 new peaks in the treated water that weren't in the raw water. And so that meant that not only was the treatment plant not removing everything, but he was actually creating new things. And he was a smart guy, a chemist, biochemist, and he figured out that what was happening was the chlorine was reacting with naturally occurring organic matter and forming these compounds known as trihalomethanes. And they were halogenated compounds that we thought, oh, these are going to be likely to have some toxicity associated with them. Later presumed and determined to be carcinogenic, or at least likely carcinogens. Then the US EPA jumped to action in remarkably fast form in only about 5 years, which is like lightning speed. And they established a regulation for trihalomethanes in 1979 based on a presumption of a link ultimately with bladder cancer in humans. It was shown through epidemiological evidence. All right, so Chapel Hill. Chapel Hill Des was already there, and I joined a couple years later. And our mentors, Charlie O'Melia, as mentioned already. Phil Singer was my advisor and a co-advisor for Des as well. And then other really important people for both of us are Dan Oken and Russ Crispin, who are early researchers and workers in the engineering field in environmental engineering. And Des and I worked hard at the bench like PhD students, working with our analytical instrumentation, Des with his Coulter counter and me with my total organic halide analyzer. And you know, as a PhD student, you are utterly devoted to your laboratory work, if you're a lab-based person. You work hard with these instruments. You kind of eventually become one with them. You might even lose your sense of identity between instrument and person. And oh yes, and there are other people there too, I have to tell you. But as you start to lose your identity, you know, there's this period where you how it is with a spouse or an animal, you start to look like them. This happened to Des. And Alice, being the wonderful spouse that she was, she kind of went along with it too. Okay, so how do these things form? The trihalomethanes are these compounds down here. They have 1 carbon and 3 halogens associated with them. And where do they come from? Well, as John Roque figured out, they start out, the carbon comes from the natural organic matter that's in water, comes from plants. We hit it with chlorine to disinfect, not because we want to react with the natural organic matter, but we want to inactivate pathogens. Well, that chlorine smashes the natural organic matter into pieces. Some of it ends up as the trihalomethanes, some of it ends up as other organic halides, and some of it is just slightly oxidized organic molecules. But chlorine is like a hammer that breaks things up and introduces chlorine into the process. And bromide is often present in natural waters, and so that becomes incorporated into the trihalomethanes. That's where the bromine comes from as well. Those are the disinfection byproducts down here. These are among them. Also, some of these over here. And what I'm going to call the precursors are just the organic molecules within NAM that react with chlorine and form these disinfection byproducts. All right, so that's a little bit of background on this. Where does the NAM come from? Well, it comes from nature. It comes from decaying plant matter, from primary productivity of various sorts. Is my view, an engineer's view, an aquifer and a watershed and plants on the upper soil horizon that ultimately leach organic material into the soil, and it sometimes can end up in the groundwater that then flows into surface water, bringing with it maybe some nutrients that feed the growth of algae. The algae lyse and give rise to more organic matter, and then the water supply uses that lake as a raw water, and there's organic matter there. And when we have a rainstorm, what happens is you have more overland flow. You've got a higher water table. The fish turns into a shark, whatever. And you've got more growth of algae, too. And so more organic matter. How do we measure organic matter? We measure it with a total organic halide analyzer. Those of you who have used a TOC analyzer know what I mean when I say the bane of your, or a scourge or bane of existence. These things are a pain in the neck, but they're really important because they give us a measure of how much organic carbon is present in the water. And where does that come from? Well, the carbon that's present in the natural organic matter is embedded in a mess of molecules that are very difficult to deconvolute. And the easiest way to know how much we've got there is to take all that carbon, combust it in the presence of oxygen, turn it into carbon dioxide, and then measure the carbon dioxide over here. And so we can do that quantitatively, pretty much, and that tells us how much organic carbon is present. So I'm going to show some results, some graphs of organic carbon. And it can be total organic carbon if we measure without filtration, or it can be dissolved organic carbon if we measure after filtration. So TOC and DOC are 2 terms that I'm going to mention. All right. Now, superimposed over this is the observation lately that levels of DOC or TOC, but I'm showing DOC here, dissolved organic carbon, are going up in many places around the world with time. This is probably in a very extreme case right here, but these are all three of these lakes are showing increasing concentrations of DOC just in the past 30 years. And these happen to be from Ontario, but we've also noted this phenomenon to a slightly lesser extent in other parts of the world. And for us, for me in New England, we see it there as well. It's superimposed over other things like annual cycles, but here are a couple of examples of waters that are used for drinking supply. This happens to be Groton, Connecticut, which shows a nice sinusoidal behavior, an annual heating and cooling or seasonality. But if you look at the long-term trend, it's going up. And over here, you've got the Boston water supply, which has ups and downs for various reasons. But over the past 10 years or so, we see it going up. And up here, we have Springfield, Massachusetts. Again, we've got peaks due to some intensive storms that came through, but the long-term trend is increasing too. And while it's a little subtle here, it's much more noticeable for operators of water treatment plants. They're the ones who've noticed this first. And it's only because they are dealing with this day in, day out, and that they have to meet the disinfection byproduct regulations. And they're having more and more trouble with time meeting those regulations. So there's probably some subfraction of the organic carbon that may be increasing faster than the total dissolved organic carbon. So this is attributed to climate change of some sort, we think. And these long-term changes. Well, what's causing these long-term changes that we're seeing all across the northeastern US, many other parts of the world, all across northern Europe, and maybe other places as well, because it can be pretty subtle, but it's definitely happening. And one is the possibility of air pollution. And this is a strange case of unintended consequence of something good. So we have been doing a pretty good job of shutting down acid rain. Acid rain coming from combustion of sulfur and nitrogen oxides that are acidic, that end up precipitating and lowering the pH of surface waters. But by doing so, we've created some problems, and I'll mention a little more about that in a minute and why. Also increasing nitrogen deposition, and there's some places where that's occurring as well. Climate change causing higher temperatures, more intense rainfall, longer periods of drought, shifting terrestrial plant species, moving basically further north in many cases, changing solar radiation, and then the presence of invasive herbivorous insects too. And what are the secondary effects? Well, one of this is of less acid precipitation. That means the pH is now rebounding. It went down with acid precipitation. Now that we've cut back on it, it's rebounding back up. That causes a phenomenon known as lake recovery. And when that happens, we have a change in the natural organic matter and it becomes more soluble. Another one, algal blooms are more frequent in many places. Peat solubilization, that is peaty soils for a variety of reasons related to changing climates and changing hydrology are becoming more soluble or disappearing. The peats are disappearing into the water. Faster and more complete NOM, natural organic matter export, wildfires, and this rapid defoliation due to the herbivorous insects. So it's a pretty complex set of processes that are leading us in a bad direction right now. I'll show you a couple of examples. Here's one. We've been working with the city of New York, looking at what happens during storm events in one of the major reservoirs, the Neversink Reservoir, and the river that feeds the Neversink Reservoir. And this happens to be one single 2-day period in 2019 where we were monitoring the flow and the concentration. The flow in this river is shown by the blue line. The concentration of dissolved organic carbon are the red triangles. And what's really important, well, let me say first, you would think that when you have a huge amount of additional rainfall and rain, you think of rainwater as relatively pure. You'd expect the rainwater to dilute the solutes in the water, in the river, make it less concentrated. But what's happening here is making it more concentrated. And why is that happening? Because it's flushing the organic carbon that's up in the watershed that normally would be perched and separated and not not hydraulically connected to the river and connecting that and flushing that stuff out. And at least that's one interpretation of this. So the overall, what we call loading, the amount of organic matter that's going into this reservoir is the product of the concentration times the flow. And that's this line up here. So over the course of this one storm, in just 12-hour period, you have an increase from 5 kilograms to 1,665 kilograms per hour. And so that's an indication that storm events that are occurring more and more frequently and more intensively are adding huge amounts of organic carbon to our water supplies. So that's one little piece of information and evidence. We expect these increased storm events to occur across the eastern U.S. And even down into Texas over here, but especially across most of the eastern U.S. And so that could be an important factor for some of the observations that have been made. Another one is this lake recovery that I mentioned. So in lake recovery, once again, during the onset of emissions of acidic gases, and that onset occurred in different places depending on where the plumes were coming from, you would get a drop in pH, and in addition, at the same time, you would get a drop in the dissolved organic carbon. And there are good chemical reasons for this, one of which is the lower pH means the organic matter has less charge on it, and when it has less charge, it tends to be less soluble and ends up more in the sediment and not in the water column. Then, once we started doing a better job of reducing the acidic emissions, you see this rebound effect. And these happen to be, by the way, for those of you who are wondering, these are estimated dissolved organic carbon levels based on the sediment record, because we weren't measuring dissolved organic carbon back here. So this is trying to recreate the historical record of it. But there's a lot of evidence that shows that this rebound effect is occurring. And where would that occur? Well, again, regions mostly in the eastern U.S. that have been receiving acidic gases for years and years and now are not so much. And the recovery is delayed in different places due to naturally occurring processes, natural alkalinity of the soil and so on. But there's evidence that it's going to eventually occur everywhere. Another one, the gypsy moths. A third. I don't have enough time to go through all these, but there's some interesting case studies. The gypsy moths have been slowly expanding out from 1900 to the present across the Northeast. The zone over which the gypsy moths are expected to ultimately expand their range, areas that are receptive to the gypsy moths are, again, a good portion of the east and portions of the west as well. And what happens with the gypsy moths is that they causes rapid defoliation plants and rapid solubilization of the organic matter that would otherwise possibly degrade in the watershed, but that organic matter gets flushed out into the rivers and lakes. And there's and I think on this next one, whoops, did that wrong. There is, Bob Cortman wrote a paper just in the past, 2019, a couple of years ago, documented this and made connections between gypsy moth populations and areas in the Northeast where there was an increase in DOC. And he made this argument that that was the reason. So whatever the reason is, this seems to be happening, and we have to be concerned. And it might not just be the DOC that's increasing. It might be, the DOC just might be the canary, and the real concern might be some of the constituents that make up that dissolved organic carbon that are especially prone to forming disinfection byproducts. So I'll return to that. So DOC is, and this is one of my messages that I want to leave with you, is a very blunt tool. If you look at how much organic carbon is in a typical amount of trihalomethanes formed versus the total amount of DOC in that water, there's only about, 0.25% is in the trihalomethanes. The remaining 99.75% is not. So why would one correlate so well with the other? You'd have to ask. And in a way, using DOC as a measure, as a proxy for this these disinfection byproducts that we do all the time is a little bit like if you went to the doctor and were sick and the doctor gave you a prescription for 100 milligrams of medicine, but it didn't indicate what the medicine was. He said, well, you ask, what is the medicine? What are you giving? What are you asking me to take? He said, well, whatever they give you at the pharmacy. Doesn't matter. It's 100 milligrams. Well, DOC is not DOC is not DOC. And if you've got 2 milligrams per liter DOC, it might be very different in one location than another. We need to know more. We need to be a little bit savvier in understanding this. And to give you an idea what I mean, if you take a look at a sample of naturally occurring organic matter from a lake or a river that might be used for drinking water, and you run it through an ion cyclotron resonance mass spectrometer, Fourier transform ion cyclotron resonance mass spectrometer, which I've never done, but there are people who do this. And you look at, this gives you super high resolution of mass, allowing you to identify tens of thousands of different unique empirical formula, unique structural molecular types. This is one way of expressing and showing these results on what's called a Van Crevelen plot, which has the hydrogen to carbon ratio on this axis and oxygen on this axis. So the further up you are, the more hydrogen it's got in its molecule. The further to the right, it's got more oxygen. And you can see that there is a mass of points or of dots here that are divided up into different zones based on the type of molecules in nature that might fall into these categories. But keep in mind, so lignin is here, and tannins are over here, and lipids and proteins and so on. But this mass right here is the actual observed natural organic matter. And so each one of these points represents a unique empirical formula. And that means then that you've got potentially 10 or more isomeric forms within each point. So we're talking about tens of thousands, maybe 100,000 molecules. So it's complex. It's not just a single stuff. And if you take one of these, let's take one of these from here in the lignin zone, and you look at what happens with this and reacts with chlorine, well, it's awfully hard to tell. We go to the organic chemistry literature now to understand how chlorine reacts with organic molecules. And if you go to an old organic chemistry textbooks, do people still use textbooks, don't you? So anyways, when I took organic chemistry, I had in the section that talked about chlorine reaction something called the haloform reaction, which started with a molecule like acetone. And it was a well-characterized reaction that goes through several steps, forming one intermediate where, and X, by the way, is chlorine, and in this discussion at least, is one monochlorinated, one chlorine, and then it goes through a few more steps and forms one that has two chlorines, a few more steps, one that has three chlorines, and eventually it hydrolyzes to form chloroform, or one of the trihalomethanes. So this simple molecule has 1, 2, 3, 4 different chlorinated products that are reasonably stable. That's the simplest of molecules. If you take one of those molecules of the lignin type NOM, like this, and add chlorine, who knows how it gets to chloroform. There are just so many different routes one could take, and so many different intermediates you could form. It's mind-boggling, and that's just one of 10,000. So we've got a problem that's far more complex than we normally represent it as. Okay, and one of the ways of doing this is I like to show this iceberg analogy, where we have most of the disinfection byproducts are below the sea level and the dangerous part of the iceberg that we don't see usually. The ones that we can see are these two that pop up here that are clearly evident because we have analytical methods that can see them, and we've got a regulatory agency over there that can see the little pieces that are sticking up. But we also have the researchers who are plunging the depths from the utilities, from research universities, and who are identifying more and more of this iceberg as we go down. We've got maybe 700 different compounds that we've identified to this point, but there are probably thousands more that we haven't, that were still to be identified. And some of the names are shown over here: haloaldehydes, haloacetamides, haloacetonitriles. We have the trihalomethanes, we have haloacetic acids, and so on. And they keep going as we learn more and more. And the key is not so much what's there. But the key is, how toxic are these? And do they all have the same toxicity or not? Are they all the same toxicity as the trihalomethanes, let's say? Well, the answer is no. It's pretty clear. Now, exactly what kind of yardstick you use to measure toxicity is a really good question, because we don't experiment with humans. It's generally not a good idea. But we will use animal models. We will use laboratory toxicity analysis. And one is with Chinese hamster ovary cells. And this is Michael Pleva's work from the University of Illinois, who has looked at many of these various disinfection byproducts and found that the range of toxicities are 1, 2, 3, 4 plus, over 4 orders of magnitude different. And some of these have such low toxicities, some of the trihalomethanes, you can't even measure them. And there are others, I'm sure, to be identified that are so much more toxic that they're off scale and just haven't had a chance to test them. So with 4 orders plus of magnitude difference in toxicity, we need to be mindful of what they are and not just treat them as trihalomethanes or one type of disinfection byproduct. And what we know already from at least this particular yardstick of toxicity, this is not perfect by any means, but it's one that we do have in a large database of, and so we can make comparisons, that the haloacetonitriles and haloacetamides are more toxic than the halonitromethanes, are more toxic than the haloacetic acids, and the least toxic of all are the trihalomethanes that were the original focus of the regulation. And we also know that those that are chlorinated are less toxic than those that are brominated, which are less toxic than those that have iodine. Those are the 3 halogens that often substitute into these molecules too. And as a result of this difference in toxicity, we can look at total mass of the measurable disinfection byproducts. I made a pie chart out of them. This is not mine, this is from the literature recently, and showing that trihalomethanes and haloacetic acids, another group that's currently regulated, form the major amount of measurable DBPs in terms of mass. But if you apply the specific toxicity to each one and multiply the concentration by the specific toxicity, and then remake the pie chart, you find that the majority of the toxicity is in the haloacetonitriles, which are a relatively small amount in terms of overall mass, whereas the trihalomethanes shrink down to almost nothing, as is and the haloacetic acids too. And there are a few others that are important. So I'm going to mention a little bit about the haloacetonitriles, because we think they're toxic both within the Chinese hamster ovary assay, but also there are toxicity models that say that they're likely bladder carcinogens too. Okay, so how do we control the risks? And this is another important piece of this too, of course, because we don't want to just say, oh, there's a problem, we got to do something about it. We as engineers want to take action. And we can do this through watershed management, through selection of sources that are less likely to form toxic byproducts. And then there's the use of in-plant processes to remove the precursors. When we have no choice, we've got the best source we possibly can, we've done all we can to protect the watershed and prevent export of a lot of this organic carbon that is of concern, we still can try to remove as much during treatment. And that includes oxidation of the natural organic matter or removal of it through various processes. And that's this conventional treatment that I was talking about. There are other things we can do too. We can delay the point at which we add chlorine to disinfect, change it from chlorine to chloramines. That has an impact as well. And remove disinfection byproducts after formation, which is a little hard and not so successful. So here is what we generally have been doing now for many, many years is conventional treatment. And I want to mention Des because Des quite literally wrote the book on water treatment. This is the textbook that we at UMass and around the country have been using for years and years. Even prior to the publication, we had drafts that he would send us. And so thanks to Des, we are teaching this and we are understanding this very, very well on a fundamental level and teaching it to the next generation of engineers. And this is a process that has been worked for a long time and is very successful, but there's still more that we can do. And this process includes some sort of pre-oxidation, rapid mix after addition of a coagulant, this is called coagulation, then some sort of gravity settling or flotation, some separation of the floc particles, possibly an intermediate oxidation, granular media filtration, and then final disinfection with chlorine, or usually with chlorine first, and then if we are going to use chloramines, we'll add ammonia a little bit later after a free chlorine contact period, and then off to the homes in the distribution system. Now, how do we evaluate this? Well, we want to make sure that these processes are doing a good job of removing microorganisms, especially pathogens, and so we do that by looking at treatment conditions that are effective for removing specific pathogens. We make sure that we're protected from chemicals that are in the raw water and the plumbing by testing of some of those specific chemicals and making sure they're removed. But when it comes to the disinfection byproducts, we're not doing such a good job. We look at the trihalomethanes and the haloacetic acids, which are probably not the ones that we're concerned with. And we also look at the dissolved organic carbon too. But that's, as I mentioned, a very blunt tool. So we can do better than this. For example, when we do the first step of treatment with an oxidant, in this case ozonation, we find that ozone has almost no effect on DOC, dissolved organic carbon. So we would say, oh, well, it's not really doing anything. Why do it? But then if we look more carefully and we try to deconvolute what's in that DOC and look at the specific precursors that give rise to different disinfection byproducts, we find that, in fact, it does remove the structures within the DOC that form trihalomethanes. It oxidizes them a little bit so they can't produce as much trihalomethanes. If we're looking at the dihaloacetonitriles, it does a great job of those, removing those. Dichloroacetic acid, no, it doesn't do much there at all. And then there are some, like trichloropropionone, that are actually enhanced with ozonation. So this is a complex picture, and we can't just look at one yardstick. We have to look at the big picture of toxicity in this case. So look at the individual parts. If we look at how this works in different locations, different types of waters, we see, well, some, Elgin, Illinois, Newport News, Virginia, Waco, Texas, pretty good. Not too bad in terms of removal by ozonation or destruction of these various precursors. But then there are other places, Dallas, Winnipeg, maybe not so good. But there are some similarities too here. And so once again, it's emphasizing the fact that natural organic matter and DOC can be the same from one location to another in terms of milligrams per liter organic carbon, but the way it behaves, it can be entirely different. And that's because that mass of molecules is different, even though the total amount is the same. If we look at coagulation, we've known for a long time that you can remove maybe 50, 60, 70% of the dissolved organic carbon if you add enough coagulant and if you have the right pH range. And if you do that right, you'll find that in Des's book, in fact. It's very clear. But that's the overall DOC or the TOC. If you look at what coagulation does to individual precursors, and this shows, this black line, by the way, is the TOC, or DOC rather, as a function of the amount of coagulant dose. And you see, once again, you deconvolute that and look at the individual components that we can do using chlorination tests. You see that some are removed very well, and some are removed not so well as compared to the DOC. This is true in actually both graphs. One is before ozonation and one is with ozonation, one is without. The effectiveness of coagulation is different for each. And then there's another complication too. So we have to think about bromide. And so as you remove DOC in water treatment, you'll increase the ratio of bromide to DOC. And the reason that's true is that coagulation generally doesn't remove bromide. So if you're increasing or keeping bromide the same and decreasing the denominator, you're going to increase the ratio of bromide to DOC. That's generally true. When you increase the ratio of bromide to DOC, that means bromide it's more effective, more competitive, and tends to populate the byproducts more with bromine. And that means, from the Chinese hamster ovary tests and other tests, that you're increasing the toxicity of that group. So we want to remove the precursors, but when we do, we end up increasing the toxicity of what's left. It seems like there's no win here, but there really is. We just have to understand it and quantify it. And you can see this is some actual data from a recent publication showing increases in the specific cytotoxicity of different groups of molecules as you increase the bromide to DOC ratio, which happens when you treat. So another pain in the neck. And then there's the question of what happens after it leaves the treatment plant. And so we hit the water with a little bit of chlorine, a little bit of disinfectant, and it continues to react until you pour your tap water, your glass from the tap, and drink the tap water. There's still chlorine in there. You can smell it, usually. Especially if you've got free chlorine in your system, you can smell it. And that reaction has occurred from the moment you added chlorine at the treatment plant to the moment you drink the glass of water. So that time frame can be a few hours if you happen to live near the plant. It can be a day or two. In the case of where we live, we're about a day away from our treatment plant. But it can also be as long as a week or even 2 weeks. It's amazing how long the water will sit in the system before you consume it or use it. And we know from laboratory experiments that as long as you have a chlorine residual, the trihalomethane level keeps going up. Even a week after the reaction started, it's still going up. So what does that mean in terms of best place to live in a city? Here's the city of New Haven, Connecticut. We studied New Haven, Connecticut a number of years ago. This is the water main map of New Haven. Here's the Google map of New Haven. And so what you see here is this is the little bit of Long Island Sound here, and that corresponds with this inlet right here. And this is North Haven up here, and North Haven up here, North New Haven. All right. So what we did is we did testing, we did some modeling, hydraulic modeling and chemical modeling, and came up with a map based on the individual pipes showing the levels of trihalomethanes in the New Haven system. And then, typical, this happens to be one snapshot one day, but it's typical. And what you find is, well, you've got 2 water treatment plants feeding into the system. I know here in Austin we've got 3 plants, I think, feeding into your distribution system. Well, New Haven has these 2, Lake Saltonstall and West River. And the areas near where those treatment plants are feeding in have the lowest levels of DBPs, in this case trihalomethanes. And they feed into the system and eventually end up downtown where the levels are higher, maybe on the order of 30 to 40. But the highest ones, the screaming high ones, are near this Mill Rock tank over here, which is a large elevated tank that stores water out in the system. The water fills up that tank and it just sits there. It'll sit there for days and empty and fill and empty and fill. And then finally at some point it fills quite a bit and supplies water to this whole neighborhood. And that water is old. And that's been sitting there and reacting, and that has the highest levels of DBPs. So you might want to think about where you live with respect to not only your water treatment plant, but any elevated storage tanks you know of too. So this says that not everyone is treated the same. And there are concerns that these high-level areas may be environmental justice areas too. It's classic that this has happened. Okay, but that's not the whole story. So the trihalomethanes increase and never stop increasing. But many of the more toxic ones, like the haloacetonitriles, will increase, depending on pH. Let's follow the green line here, though. This is pH 7, I think. Will increase to a point, maybe 24 hours, max out, and then drop from that point onto a week. So in that case, that older water is maybe less of a concern because the level of toxicity is lower. So what happens with this? Well, the dihaloacetonitrite continues to react with chlorine, forming dichloroacetamide, which has some toxicity too, and then finally to dichloroacetic acid, which has almost no cytotoxicity that we know of. So if you look at the trajectory of a precursor of dichloroacetonitrile that's treated in the water and then goes out into the system, that has a toxicity that's going to max out at pH 7 at least, at some intermediate contact time, or water age of maybe 20 hours, maybe almost a day. And then when you get to the very end, like that tank effluent, way out a week or so into the distribution system, the toxicity is pretty much down to zero. So the thing that's happening now in the country, of course, for a long time is we've tried to control THMs. So we tried to keep those long water ages from occurring by changing the flow of water and moving the water through the system faster. So you minimize this and you maximize that. And maybe we're doing it exactly the wrong way. Maybe by spending what amounts to billions of dollars across the country trying to remove trihalomethane precursors, trying to minimize contact time in distribution systems, we may be, in fact, not helping matters, but possibly making it worse. And that's because we're not looking at the big picture, the whole thing. Okay. Another thing is, of course, is this question of if we do control trihalomethanes, and this is a data set across the country from a number of years ago, showing trihalomethanes on this axis and dichloroacetonitrile on this axis. If we do control the trihalomethanes down to the standard, which is 80 micrograms per liter, we still have a huge range of haloacetonitriles, dihalocetonitrile. Order of magnitude difference. And that's the toxic one, we think, not the trihalomethanes. And so, once again, we really want to make sure that we're paying attention and understanding the difference between compounds that are easy to see and easy to measure and part of a regulation and compounds that are really more toxic. Okay, so what I want to leave you here with is a few conclusions. One is, if we're going to try to minimize toxicity due to DBPs and solve this problem that we started a long time ago to solve a bigger problem. And we solved that bigger problem of pathogens in water. But we want to solve the smaller problem too, which is the one of cancer causing chemicals. Then what we want to do is we want to monitor and control that full spectrum of disinfection byproducts, not just the trihalomethanes. And not just that outlier group, that unusual group that is easy to measure. It was regulated early. We want to consider the other compounds. And we wanted to develop toxicity profiles for those other compounds too. And then we want to view natural organic matter as the complex mixture that we know it to be. We want to measure subgroups of the natural organic matter and improve our understanding of how or where it comes from and how it persists in the environment. And then finally evaluate the options for watershed management and treatment to remove these things as best we can. And this falls onto the future organic geochemists to come up with better ways of understanding the origin of natural organic matter and specific compounds and their environmental fate, like lignins, for example. That we need analytical chemists to help understand and develop these deep methods to quantify these things. We need toxicologists to better refine our knowledge of toxicology of these specific compounds and human health impacts. And finally, we need environmental engineers to better understand the best way to treat these and to remove these subgroups of NOM that are causing problems. Okay, so I just want to thank a lot of sponsors and people who have helped with this work over the years. And in particular, a couple of my colleagues at UMass, Jim Edswell, John Tobiasen. Some of you know these two, who I've been working with for 40-some years at UMass and before. And of course, we have the mentors for all of us, Charlie O'Melia, Phil Singer, and Des has really been not only a colleague, but a mentor as well. And student contributors, and there are always a lot of them, and way too many to name right here. But what I would like to say is I'm especially thankful for the people here at UT Austin. It was back in 9 years ago that we started to create a national center for small systems between the two universities, UMass and UT Austin. John and I got a call for a new type of EPA center. And the first thing we did when we saw it is we got Des on the phone and said, would you be a part of this? And would you bring your colleagues here as part of it? And he said, I'll see what I can do. And it worked out beautifully. The UT Austin faculty became the heart and soul and the engine of this center that we worked on together. And it's been great to get to know them, and I realize that it's such a very special group. And say a few words about Des too. This is really a pleasure to be here. There are just a handful of people around the world who are viewed as leaders in the environmental engineering field, thought leaders and leaders in engineering. And among that group, I think Des stands out for his personal integrity, his sense of civic duty, his wisdom, his kindness. And it's been a pleasure to work with Des through these years, starting with the mid-'70s, and I know I will continue. I'll have a chance to continue to work with Des in many ways, especially through consulting projects. And I'm so happy about that. Very happy to be here at this place, this time with all of you too. It's this very special program that Des has helped to create. And then finally, I want to say in closing that I know that life is a team game. It's a team sport, and I know in my own case, my wife Kathy has supported and enabled me to do things that I could never have done otherwise. And I know for Des, the same is true with Alice too. And so I want to thank them as well. So in closing, I'm just very happy to be here, and I'm happy to answer any questions you might have. Thanks.
We have time for questions. I'll run as fast as I can to where you are once you raise your hand. So raise fast. Who's going to start us off? Carrie. I didn't have to go very far at all.
Yeah. So one of the questions that I have, of course, I look at the microbes in water, and of course, there's always this tension between disinfection and, making sure that the water is safe to drink from a pathogen perspective. Can you comment on that as you've seen how this is played out?
Right. Well, I think there's been a lot of discussion of what level of disinfection do we need?
Exactly. Yeah.
And how do we design our treatment and distribution systems to make the best use of that optimum of disinfection? And I think in this country that ship has sailed a little bit already.
Yeah, exactly.
We've designed our systems to be somewhat dependent on chlorine and heavy doses of chlorine. And so I don't think we want to backslide on that. We've seen what has happened in other parts of the world when this has happened, and it's not a good thing. And so we always have to be, I think, mindful of the great triumph of, that goes back to the early days of conventional treatment, starting in New Jersey of all places, where they first started adding chlorine in Jersey City water. And I think we want to continue to do that. We just need to make the most of it, given that we have to add chlorine.
So you have to find the sweet spot, basically.
Yeah, that sweet spot.
We get both.
Mm-hmm. Yeah, right. Oh, right there.
Sorry, fell down on the job. Working on travel arrangements.
So I think I should know this, but I don't. How do you measure precursors to specific DBPs?
Yes, okay, good. Thank you for asking that, because that's something that I really didn't have a chance to cover. So it's actually a pretty simple method. we don't know what those precursors are. So how do you measure something you don't know? Well, what you do is an empirical test. And you take a water, you add chlorine at a certain pH, at a certain chlorine dose, allow it to incubate for a fixed period of time, usually a day or 3 days. You quench the chlorine and you measure just empirically how much of each type of disinfection byproduct was formed. And that's really at this point the only way we can do it. Some point in the future, maybe we'll be able to measure really the compounds that are creating those disinfection byproducts. And this is the guy who might help us do that.
Thanks, David. I'm more on the air side, but I really enjoyed and I found this lecture absolutely inspiring, especially that I've observed when looking at the air composition that we are biased by the most abundant compounds. But the most abundant compounds are not always the most toxic ones. Mm-hmm. I really liked your approach when you expressed toxicity by concentration divided by LC50. Mm-hmm. And I also, I was thinking that those byproducts that you were showing, many of them are really volatile. For example, dichloroacetonitrile has boiling point of 110 degrees C.
Mm-hmm. Right.
So I'm wondering if one of the future approaches could be actually by looking at the gas phase above water to monitor those byproducts in real time. I wonder what you think about it.
I think that's a great idea. I really do like that because I think given the technology that's now available for doing this, I think it gives us a chance to measure in real time something that now we struggle to do with lag periods of a week or more in the laboratory. So I love that idea, and I hope it can be pursued. Yeah.
Thank you.
I'm coming, Eric.
Well, thank you very much for the presentation. Trying to understand the complexity of NOM, how does that change over time? Because you said that it was influenced by weather patterns. How are we going to understand that as it develops over time with different influences?
Right. Well, right now we've got the empirical tests that I was just talking about, so that we can do more than just measure TOC or DOC with a little box that you buy from a vendor. But we can do the chlorination and look at how the individual disinfection byproduct formation changes as DOC changes in, for example, the Neversink River. And we've started to do that a little bit during a storm event, or maybe over time during a defoliation event. We can do that. Eventually, we'd love to be able to identify and monitor the changes in individual concentrations of NOM structures. But that's going to be a little further down the road, I would say. Yeah. Yes.
Thanks for the great presentation.
Thank you.
Early in the presentation, you had showed that distribution of different disinfection byproducts. I might have missed this, but is that solely or most significantly factored by the organic precursor distribution, or is it pretty much that distribution is factored by other things like residence time?
Yeah, okay, good question. Yeah, it is. I think it's a combination of the two. I think, though, the overall source of the variability is in the differences and concentrations of the individual NOM compounds. But certainly the conditions under which you chlorinate the water affect that. So we try when we do these precursor tests to always keep to the same set of conditions so that we take that out of the equation so that that's not affecting it. And so the hope is that we're really reflecting the original mixture of NOM compounds. Yeah.
Thank you for a wonderful presentation. In Austin, we use chloramine instead of free chlorine.
Yeah.
Does that help?
Yeah.
It should, I hope.
Yes. Well, it helps. It absolutely helps with meeting the standards for trihalomethanes and haloacetic acids. Because what happens with chloramines is you add a little bit of free chlorine to get adequate disinfection. The engineers call it CT, concentration times time, which is an indicator of level of disinfection. And then you add ammonia, which then converts the chlorine, the free chlorine, into usually monochloramine. And that monochloramine seems to be incapable of adding a third halogen to any particular carbon atom in the NOM. So it stops the reaction at 2 halogens and slows down everything else as well. And so since most of the regulated DBPs are trihalogenated, then you don't get any more THMs. It stops it pretty much dead. You stop the trihalo part of the haloacetic acid. You have a little bit of an increase in dihalo, but not much. The downside is that some of those toxic ones that I showed, like the haloacetonitrile, are formed by chlorine but also destroyed by chlorine. And once you form them, and if you then convert the chlorine into chloramines, you're not going to destroy them anymore. And you can continue to form more. So when it comes to the regulated DBPs, it's great. It works really well, and it's an inexpensive solution. When it comes to toxicity, it's not so easy to say. Yeah.
Hi.
Hi.
Similar to that, so we know that there's the 2 major compounds that most water utilities are, concerned about. Can you say also, like, how good are those as a proxy for the other ones that we can't measure or don't measure? Like, if we have high THMs, right. What does that say about the other ones? Can I say, oh, okay, we're high in this, so we're probably high in the other ones too? Or
yeah,
doesn't work like that?
Oops, wrong one. I was going the wrong way here. So let me show you that. Here's the answer. If it was a perfect proxy, this would give you a single line, all the points right on that line. So it's less than perfect. And this is just one of them. And I suspect it's even worse for others. So the answer is the idea, well, when EPA established the original regulation for THMs and then revised it a bit later, the feeling was that, okay, we know THMs may not be really the problem, but we suspect they correlate really well with the compounds that are the problem. So the answer is no, probably not. Probably not. However, having said that, if you don't have any organic carbon in your water and you're chlorinating, you're very unlikely to form any organic disinfection byproduct. You can't. So at the very extreme, it probably does work. But in the middle, it's probably not very good. Yeah.
Excellent talk. Thank you so much. So one of the issues I've run into in pilot plants I've worked with over the years is that there's obviously a reactive component of the DOC. It's not just DOC. Right. And what you're trying to deal with is take out the reactive DOC. And I have seen repeatedly that if you do a good job with sweep flock and the right coagulant, because you can't just use what we use here, this is what we use. We've always used alum or whatever it is. You have to find, and often what I have seen is ACH, for example, is often very good with the reactive component reduction. It doesn't maybe change the big number that much, but the reactive component, and had good results, but yet because of this differences of the DOC where there's these nonpolar and other varieties out there in the DOC, you don't always get the reaction you want, which is that you could free chlorinate and still get by with compliance because you've taken out so much of the reactive component. I'm just wondering what you're thinking about this issue about moving us forward in terms of the conventional processes, looking more at sweep flocks and more at the reactive component identification.
Yeah, okay. So I think in terms of coagulation and flocculation and removal, you certainly do probably a better job of removing the precursors of concern than you do the bulk TOC, like some of those graphs I was showing with coagulation. I think that's absolutely true, and I think that's going to be true for almost all waters. But it's never perfect, of course. So if you can get, let's say, 55, 60% removal of TOC, you might get 70% removal or 75% removal of THM precursors, but that's probably about as best you can do and without and even with adding, you can always do a little better with slightly higher doses as long as you're controlling pHs correctly. But you end up producing so much sludge, you want to go somewhere else for that. So I think it's conventional treatment, coagulation, with what we sometimes call enhanced coagulation, is always going to be a key element of our arsenal in controlling this. But we've got to think of other ways too, and we've got to be sure that we are doing good with what we're doing and the money we're spending on treatment, and it's actually helping for sure, rather than just spending money to meet a regulation.
Thank you. So before we give Dave another round of applause, I just want to make an announcement that there are some refreshments outside the door and down the hall a little bit. Please feel free to partake and enjoy them, and I won't hold you up from them anymore. And thank you again, Dave, for an incredible talk.
Yeah. Thank you.